Now, do you have any questions so far?
No.
Right. So let's move to the first lecture, lecture 1. So this is just an introduction lecture, just to see what we're really talking about. So our course is called Data Structures and Algorithms. Okay. So in this lecture we are going to see what did the word algorithms mean. So the word algorithm comes from the name Al-Khwarizmi, okay, which is who is a very well-known mathematician. An algorithm means just a well-defined procedure for solving a problem. Okay, that's what an algorithm is. It's just a well-defined procedure for solving a problem. In its simplest of meanings, a well-defined procedure for solving a problem. So if we have a problem and we have a procedure which is not well-defined, we cannot call it an algorithm. Okay, that's all what an algorithm is about. Now, when we talk about algorithms, we have 3 properties. We call them definiteness, finiteness, and efficiency. Okay? So, an algorithm must be definite, finite, and should be efficient. So, what does it mean to be definite? So, an algorithm is definite if each step, an algorithm must be definite, and this means that each step of the algorithm must be precisely defined. Okay? It must be precisely defined. So there is no ambiguity. Okay? We will see examples on these characteristics. Which means if I describe to you this, we said an algorithm is a well-defined set of steps to solve a particular problem. So if I tell you a set of steps, and after you hear them you are unsure, then that's not really precisely defined. It means there is some ambiguity. Ambiguity just means when you really don't know what's going on, okay? I tell you something, but you have more than one interpretation. You understand it in one way and also in another way. This is what ambiguity means. Now, finiteness, the algorithm must be finite. It must terminate after specific number of steps or a specific time. So an algorithm which says while true, do this, that's not really an algorithm because it doesn't finish. Okay? Efficiency, an algorithm must be efficient. True, do this. That's not really an algorithm because it doesn't finish. Okay? Efficiency, an algorithm must be efficient in the sense that it should solve the problem and it should solve it in a short time. Now, the word short is relative. Okay? Sometimes there are problems that we expect, that we need to solve them in less than 1 millisecond. In this case, an algorithm which solves the problem in 1 second is not efficient. Sometimes there are problems that it's okay to solve them in 1 minute. In this case, solving them in 1 second is very good. So it's a relative metric, okay? It depends on the problem, on the context, okay? But obviously, the less time we spend on the algorithm, the better. But we cannot always have algorithms with very short times. We will see more on this when we get to the lecture on analysis of asymptotic complexity of algorithms. So again, an algorithm is a well-defined procedure for solving a problem, and it has this property of being definite, finite, and efficient. And our lives are full of problems that we need to solve. And we use algorithms unknowingly. For example, in order to make a cake, we need an algorithm which is just the recipe. So we have some inputs, ingredients plus recipe, and then we have the procedure itself, which is add sugar, add whatever. When we go to buy from a supermarket, again, it's a problem that we need to solve. So the input is we have a shopping list written on a piece of paper or memorized in our brains. The procedure is to go to different places in order to buy things, to optimize, try to scan for offers, finally pay and leave. And computer algorithms are pretty much like this. They also face problems that they try to solve using a number of steps. The only difference is because computers are stupid machines, we need to describe algorithms for them a lot more formally than we do with human beings. So because a computer will not know what to do, we need to be very precise. So we need to be extra careful with algorithms written for computers. Now, an algorithm written for a computer is just a program. You have been writing programs in the previous courses. Programs are algorithms because they solve a particular problem. A problem of saying hello world, so that's the program hello world. The problem of calculating an integer and another integer. So you write a program which basically adds two integers and outputs a third integer. That's an algorithm. So an algorithm is just an algorithm for computer is just a program. Okay. Theoretically, it's an algorithm which is a description, and then when we put it in a programming language, it becomes a program. But semantically, in terms of the two entities, they mean the same thing. Okay. So now let's see some simple algorithms and we decide how they do with a different. Now let's see some simple algorithms and we decide how they do with the different three characteristics that we saw. So algorithm 1, it says make a cake. So the input is the recipe and the ingredients. And the output is the cake, so make a cake. And I'm saying prepare a tray, put a number of eggs, put a cup of sugar, add some butter, mix, and cook for 40 to 60 minutes. So these are the steps of the algorithms. The problem with these steps, obviously, is there is some ambiguity. They are not clear. Like when I say put a number of eggs, that's not clear. That's ambiguous. How many? 1, 2, 3, 4, 10, a million? When I say add some butter, I mean what? 100 grams, 5 kilograms? Okay? So these steps this description becomes ambiguous, and hence it cannot be really an algorithm. We cannot implement it on a computer. And even a human being, I myself cannot cook this, because I don't know how many eggs. So here, this is the problem with ambiguity. So this is non-definiteness. This description is not definite. It's not described precisely in a well-defined manner. So the definiteness property is invalidated here. Okay. Now, finiteness, efficiency, we cannot really talk about them in this case because it's ambiguous, okay? Because maybe put a number of eggs, maybe it's a non-finite step, maybe it's a finite step. We don't know because it's ambiguous. So because it's not clear, we cannot really talk about the two other characteristics. So let's move on to another algorithm. We go shopping from a supermarket or a mall, and we have a shopping list and the money that we need, etc. And we want to buy stuff. Okay, so let's say the supermarket is organized into different sections. A section for clothes, a section for jewelry, a section for home appliances, etc. So what we do is we go to the clothes section and buy something from there. Go to the jewelry, buy something, return to the clothes, buy something, go to the home appliance section, buy something, return to clothes again, jewelry, home, etc. I mean, as you can see, the way we've been moving, we could have been to these places together, clothes, clothes, and clothes, we could have been to all these three places, I mean, at the same time. I mean, we could have gone to clothes section and bought a green shirt. I need some sweets. We could have gone to the clothes section and bought a green shirt and a red shirt and a blue shirt. And then we could have after that moved a green shirt and a red shirt and a blue shirt. And then we could have after that moved to the jewelry. Okay, and bought whatever we needed to buy, and then moved to the home appliances section and bought from there. So this algorithm, we can agree it is definite, although not exactly. I mean, buy a green shirt. I mean, we have not specified the size, the made, short, long sleeves, but we can say that okay, that's definite for us. So if we assume this is definite, is it finite? Yes. You buy, you finish with this section, you move to the next section. Is it efficient? No. It's not efficient, and that's because we are not being clever here. We are just moving all around the place instead of finishing one section before moving to the other section. So that's why we say it's definite, it's finite, but it ain't efficient. Is this clear so far?
Yes. Yes.
Now, let's talk about the third algorithm. So, you're okay. You want to crack the password of 10 characters. You know that your friend has got access to his or her Facebook, and you want to just crack the password and see what they're doing. And the password is 10 characters long. And you know your friend is lazy, and she or he cannot really use any other thing than small letters or capital letters and or the digits 0 to 9. So you know that if your friend has got his password, or when your friend chooses his or her password, it's going to be 10 characters, and it's going to be written in small letters or capital letters or digits 0 to 9. And then you come up with an algorithm which says, I am going to try all different combinations from all zeros to all capital Z. And I should terminate whenever one of these is going to find is going to be the password that your friend is using for his Facebook account. And then now let's try to think about the three different characteristics. Definiteness looks definite to me. It's a very clear process. What I am saying is, each time I will generate the next password in the lexicographical order. So 0 zeros, all zeros, and then all zeros except the last one is 1. All zeros except the last one is 2. And then we keep moving in lexicographical order until we move to capital Z. That's very definite, and it should terminate when the password is found. So the algorithm also finishes. Okay, it terminates. However, it's not efficient, and that's because it takes a long time to solve. Because the number of combinations is that. You will have to try that number of different combinations. Because we have 26 small letters and 26 capital letters and 10 digits. And if the password length is 10, then it's that number, which is 62, to the power of 10. So that password password cracking algorithm, in the worst case, okay, you might be lucky. Okay, you might be lucky. Maybe your friend's password is the third one you will try. But in the worst case, you will have to go through all these combinations, which is 62 to the power of 10, before before actually hitting the right password. And if 1 million passwords are checked per second, you would need about 26,000 years in order to find the password on nowadays computers. Okay? Your friend will be dead by then. So, algorithm 4, find the maximum of 3 integers. So, the input is 3 integers, and the output is the largest of them. Okay? So, the algorithm is saying, so it's simple. We have R1, R2, R3, and we want to know which one is the largest. So the algorithm says, create some variable max, compare R1 and R2, the largest of them put it in max, then compare max with R3, the largest of them put it in max, and then return max. Now, is it definite? Yep.
Yes.
Is it finite? Yes. It's gonna finish on time. Is it efficient?
Yes.
It is. I mean, I can't see how this cannot be efficient. Now we know what's an algorithm, just a well-defined procedure for solving a problem. We know that it must be definite, otherwise it's not implementable. It must be finite, otherwise we never get a result. And it must be, or it should be efficient, otherwise we're going to wait a long time before finding the result. So, this algorithm, I mean, we have seen them, we have described them, we have described them in human language so far. So, like in this example, it's really a computer algorithm, but we have expressed it in a human language. We said create. We did not say int max, for example. We said create variable compare. We did not say create variable compare. We did not say if. Okay, so we have used the human language. Now, in order to make things easy, obviously we cannot always use human language, so we are going to use pseudocode. Pseudocode, which is this one. Pseudocode is just some code, but which does not belong to a particular programming language. So Java has got its own syntax, C its own syntax, Ada its own syntax, other language their own syntaxes. Pseudocode is just some general code that we agree on. It doesn't have specific format. We just agree on some format, okay? We can say loop, we can say repeat, we can say do, etc. Okay? So it's something that we agree on. And this is in order not to get stuck at details in a particular programming language. Because what we want really is the ability to write algorithms, in the next set of lectures, the ability to write algorithms in a clear, definite way, okay, and quite quickly as well. I mean, we don't want to be standing in the lecture, writing an algorithm and putting semicolons and all brackets, etc. That's going to waste time, because that's not really the idea. This is something you will do in the practical. But when we discuss the concepts, we just use pseudocode. Okay, so the steps of designing a computer algorithm that you usually do, you think of a solution, you write it in human language on a piece of paper, or as flowcharts. Maybe you've done that in your programming courses. I mean, a bunch of squares and triangles and with arrows that shows like a statement going into another statement, with an if statement, and branching out into two different outcomes, etc. So these are flowcharts. You probably have done them. But we don't really, it doesn't really matter, because we're not going to look at the two first steps. The third step is to translate the human language or flowchart description into some pseudocode. This is what we will be doing in our lectures. and finally pseudocode goes to the final code example in Java. So for you, and you are beginners, you should go through 4 stages. Okay, that's how a beginner programmer think. You think of a solution. Obviously, everybody thinks of that, even the most experienced of programmers. Writing down steps in a human language or flow chart. This is not something that experienced programmers will do. However, when they program very big project, very big software projects, they obviously use flowcharts and human language and use cases and all sorts of things. But for programming something simple, you usually skip stage 2 if you are not a beginner programmer. You write pseudocode, you look at it and see if it makes sense to you, if you have updated all the variables, for example, that need updating inside the loop, etc. And once you're pretty comfortable with that, you go and program it. So in this course, we will describe our algorithms in pseudo language, and So in this course, we will describe our algorithms in pseudo language, and you do them in Java during the practical. So the algorithm that we have seen of finding the maximum of 3 integers, R1, R2, and 3. So this is in pseudocode. Actually, I'm cheating here. This is in Ada code. Okay, Ada is a programming language used in safety critical applications. It's nice because it's similar to Pascal. It shows lots of nice things. Okay, it's not like Java where you have lots of brackets to show things. Because we are trying to write algorithms to be understood by students, I prefer to use pseudocode, which is similar to Ada. So for you, this is just pseudocode, okay? So we have a function, find max. It takes as input 3 integers, and it returns an integer to me. The objective of this function is to find the max of R1, R2, and R3. So as we said in our human language algorithm, we define a variable max. I am initializing it to be 0. I compare R1 and R2, and the larger of them, I am putting it in max. So if R1 is less than R2, then max is this. Otherwise, max equals that. And then if R3 is greater than max, then max equals R3, and we are done. So this is the pseudocode of the human language algorithm of finding the maximum of 3 integers. Now, a question for you: Is line 4 necessary? Okay. Now, find the maximum of n integers. So basically, this is a generalization of the other algorithm. Instead of finding for 3 integers, we find it for a number of integers. So we are going to group all integers inside one array. Now, we are going to visit arrays, but we are going to visit them in the next, in lecture 3. But the way we are going to visit them is not to introduce what an array is, but really to give you some background on arrays in the context of linear data structures. So I assume that you know what an array is. So function find maximum of an array. It takes an integer array as an input, and it returns an integer to me. I am going to use this notation to denote the length of the array. So a prime length, this is going to give me the length of the array. This is just a notation. I could have written it in a different. This is going to give me the length of the array. This is just a notation. I could have written it in a different way. Okay, it doesn't really matter, and you don't have to learn it. I mean, you can, for example, let me use my teaching technology. You can write something like length of A, instead of saying A prime length. I mean, it doesn't matter. This is pseudocode, remember? Okay. So I'm defining an array. So n is the size of this array, and I'm defining the variable max again. And now what I am doing is I'm going through all the array and comparing max with each element of this array. Before that, I needed to initialize max to the first element of the array, okay? And then we compare this value with everything in the array. Each time we update the variable max if we find a variable larger or a value larger than the current value of max. And we finish when we have gone through all the array, and then we return max. Okay? So that's also another algorithm that I have written in pseudocode, just to explain, the idea. The same one written in Java looks like this. Okay. By the way, in our pseudocode, I mean, the first element of the array is 1. Or the index of the first element of the array is 1. That's why it's A of 1 here. Okay. But in programming languages like Ada or C, the first element is going to be at index 0. Okay. So that's why the max here is going to take the first value of the array, and the iteration is starting from I equals 1, i.e. the next value, as opposed to the number 2 here. Okay, there's too much colors here. Okay, as opposed to 2 in this slide. So this is just the Java version of the pseudocode. Okay, so as a summary, what we have seen is we have seen the characteristics of algorithms, 3 of them, and we have seen some human algorithms or human language algorithms written in a human language. No, that's not what I meant here. We have seen some algorithms used by human beings in their everyday life. We have seen example computer algorithms written in human format and in pseudocode, and finally in Java code. So further reading about these topics